Okay, welcome back. So this is the second to last topic for this class. Um, so we have learned a lot, many types of learning, and it would be another type of learning called reinforcement learning. Um, this term come very recently, like in maybe like 5 or 10 years. So it's very new, but it's very popular because the result is actually very good. So we'll start off with a little bit of the introduction. Um, so at the beginning, right, we learn about uh, supervised and unsupervised learning, and then we have something in between called the semi-supervised learning, right? And then today we will step away from those three, and then we will dive into what is actually reinforcement learning, right? So to reiterate, um, for supervised learning, right, your data have like input feature and label, right, x and y. For unsupervised, you only have x, right? And for semi-supervised, you have a little bit of both, but you have more of the non-label than the label one. In reinforcement learning, there is no label, right? There's no label, but there is something that is kind of related to the label. So it's not completely unsupervised, right? But it's not supervised because you don't know the correct answer, right? But you can compare whether or not this and all that is better. So in reinforcement learning, we have something called reward. That is the feedback of your action. Now, this feedback can be immediate or can be delayed, depending on your setup. So what do you mean by immediate and delay, right? So for the reinforcement learning, you want to actually make a decision, right? You have this situation and then you have to decide what to do. And when you decide to do something, there's something will have a consequence, right? Whether or not you will make something break or you will create something new. And when you do the action, right, the the situation will respond to your action in terms of reward. And sometimes when you do action, the situation doesn't change now, but maybe if you do 10 actions, right, after you do 10 actions, the situation become different. So that's why the feedback can be delayed. So your first action have no feedback because the situation doesn't change, but your 10th action will have a feedback because the situation changed. So the feedback can be right away, or you have to wait until the very end to actually see the result. And the example that in real life, we want to use the reinforcement learning is, for example, you want to fly a helicopter, right? So when you fly a helicopter, you have a lot of button, you have a lot of like stick that you have to operate, and your goal is to just fly safely, right? To fly from location A to location B. But your action right? Your action is not contributing directly to you moving from A to B, but your action will make sure that the helicopter is still flying, is still moving into the right direction, and is not, you know, dropping or falling down, right? Another example would be investment portfolio, right? So basically, you are trading stocks, right? So you have two actions. You can either buy or sell. So if you buy, well, you can some of the stock, right? And then when you sell, you uh, will gain some money back. And your decision whether or not to buy and sell at certain situation will be different, right? For example, you buy today, will you sell it tomorrow, or maybe a month later, or maybe a year later, right? So each time that you sell, you actually you actually have a chance to sell every day, right? You can sell today, you can sell tomorrow, you can sell the day after tomorrow. You can sell every day, but your action not to sell will affect your decision for tomorrow. So for investment portfolio, your reward will not occur until you actually sell the stock, right? In between, if you don't sell, your money doesn't change. But when you sell, that's when your money changes. So that when you get a feedback back from the situation. So these are the two of the real life example. Um, Reinforcement learning often used in a game, in the video game, right? For example, you play Atari game, you play like Space Invader, you play Pong or something like that, and basically the game has a set of input, right? You can press left, right, up, down. You can press A, you can press Enter. You can press space bar to shoot a laser, and each action will do something to the environment, right? Do something to the game, and for this type of game, you can actually see the reward at every step that you do, right? For example, you play Space Invader, you can see the number of spaceship that you have to shoot, right? So the number of spaceship will be your indicator of whether or not you are doing good or you are doing bad, right? If you shoot and the enemy spaceship doesn't go down, then you are doing badly. But if the spaceship of the enemy go down, then you are doing good, right? So for the first two, the reward is often delayed. But on the bottom two, the reward can be interpreted at every step of your action. So that is the example of reinforcement learning. And we want to do similar thing that human do for this type of problems, but we want the computer to do it for us. So we have to define a reward first, right? Because it's the most important part of reinforcement learning. Without the reward, you don't know whether or not your action is good or bad, right? So remember, reinforcement learning doesn't have a label. So based on this situation and your action, you don't know whether your action is good or not. There is no correct answer for the action, but there are some feedback, right? If you do this action, you get a reward, right? If you have a high reward, maybe your action is good. If you have a low reward, maybe your action is not good, right? So we have to properly define a reward so that we can, you know, apply this into the action. So we have a notation, right? We have R for reward, and we want it to be scalar. So what do I mean by scalar? It's just a number, right? There's no like vector, there's no, extra structure for it. It's just one number. And I have a subscript 3, right? So this reward will be given at a certain time, right? So for each time step, right? For each step that you are to make a decision, you will get a reward. And this reward will be based on what you do at time step T. And we want to maximize the cumulative reward, right? So basically, we want to maximize, right? So you want to maximize for all the T of the RT, right? So whatever at every step, you get some reward, but you don't care whether or not maybe this time you have a bad reward, but you might gain a better reward in the future. So our goal is just to get all the reward into the entire timeline that you are performing actions, and then you sum it up, right? So this way, you not tunnel vision to look at like your current situation, what is your immediate gain, right? So reinforcement learning look for a long-term plan, not a short-term plan. And to be able to maximize the cumulative reward, you have to be able to describe the maximization in terms of goal, right? So if you have a goal in mind, can your goals be formalized into some equation for the reward? Now, these are some example of the rewards that you can give. For example, you are flying helicopter, you will get a positive reward for following the desired trajectory, right? So you fly a helicopter from point A to point B. If you are in this trajectory, basically the path that you are supposed to take, then you get a positive reward. And you get a negative reward if you just crash, right? So it's very simple reward, but by defining it this way, right, you make sure that if you maximize the reward, what does maximize the reward mean? You want to get a lot of positive reward. And to get a positive reward, what you have to do, you have to follow the desired trajectory. And if you follow the desired trajectory all the time, what happened? You reach the destination, right? So the reward doesn't say that, oh, you get a reward when you reach a destination. No, you have to define a reward along the way, right? Otherwise, it's going to be very hard to navigate the path into the future. What about investment? Oh, Zoom. Uh, okay, I think Zoom. Can you see the number? Down. Okay. Okay, so what about investment, right? What about stock trading? So you don't have to define both positive and negative. You can define just a positive reward, right? So for investment, let's say you want to define that you get a positive reward for each dollar in a bank. So at the start, um, you have maybe like $100 in the bank, right? And then on the first day, you decide to buy the stock, right? So your money in the bank will go down. Maybe you buy $50, right? You go down to the bank. This one you get zero reward, right? Basically, you buy and then you get zero reward, right? And then in the next day, you buy another stock for $50, and then you get like your bank have $0. You still get zero reward, right? Because you didn't make anything. So we have t equal to 0, 1. And then at time 2, you sell some stock. Let's say you sell it for $23. This one you get the reward for 23. So if you want to maximize the reward for entire duration, what does it mean? It means that you want to maximize the profit, right? The profit is the money that you sell. So in general, if you don't do anything, you get zero reward, right? If you don't buy any stock, you keep your money in the bank without buying anything, you get zero reward because that's how we define the reward. But it is also possible that you start with 100 and then you buy and then you sell until you are left with $0. Right? I mean, it could be possible, or maybe like you come down to like $10 in the bank and you have no stock left, right? That you still lose money, but along the way you actually sell some stock, so you still get some profit, and the algorithm will try to maximize that. So hopefully, the total sum of the reward should be greater than 100 that you start with, but it's not guaranteed. But the algorithm will try its best, right? So what about Atari games? If you want to play Atari games, um, well, there's a winning condition, right? How you win the game, how you lose the game, right? And in games, this reward actually clearly explained in the game, so you don't have to do like a lot of interpretation. So for the shooting game, right, there will be some score, and if you have uh, your score increase, then you get a positive reward. Your score decrease, you get a negative reward. So that is very simple. So that's why when you start coding your reinforcement learning algorithm, you often start with games because the games have uh, a clear path to victory, and it's very easy to define the reward based on what is shown in the game. So that is how you define a reward. So reward is a number that will tell you how good or how bad the situation is. So the goal for reinforcement learning is to select actions to maximize the total future reward, right? So action may have long-term consequences, mean that, for example, right, in the current situation, you have action 1 and action 2. And you know that action 1, if you do it now, you will get a lot of reward. If you do action 2, you get less reward. You don't want to just pick A1 without looking in the future, because sometimes you have to do something not the best so that you can have a better reward later on, right? So we want to make sure that we maximize the total future reward. It had to be total, not just immediate. So the example would be like for the stock trading, right? You have to wait for maybe a month. You might have to wait for years for the stock to increase before you sell it, right? Because there can be many peak, right? For example, you buy it at like $5. Let's say it's go up to like, oh, it's go up more than you start with, then you sell. Maybe it can go up even more. It can go up even more, right? So sometimes you have to make sure that your decision doesn't actually close your door in the future. So at each time step, right, we are doing action, and we want to express this in a mathematical term so that the computer can understand, right? So at each step, the agent So what is the agent? The agent is maybe human or maybe a computer want to do something, right? Want to make a decision, right? So at each time step, the agent have to execute an action, AG, right? It have to pick an action. It can be ideal, like not buy, not sell. It can be buy, it can be sell, right? So you have many type of option of action. And after it do the action, it will receive the observation, OT, along with the reward, RT. So observation, what is observation? Observation is a state or a situation that the agent can see or the environment uh, answer back, right? So if you think of this as the agent, right, it's basically our brain or maybe our human brain. And then we have the world, which is the environment, right? If you buy a stock now, the observation you see would be the price of the stock, right? Whether or not the price go up or the price go down, right? So you see the price of the stock at every time step. And when you buy, you get some reward. Sometimes if the reward is delayed, you will not get it now, but at some point you will get the reward. So that is the uh, point of view of the agent. Now, the point of view of the environment, right? It will receive an action T, right? It will receive the action T. It will emit the next observation and also the next reward. And T will increment at every environment step. Right? So we have so we have the interaction between the two. So if it's a flying helicopter, your environment would be the helicopter itself and also the world, the path, like the environment of the actual world that you have to travel. If you buy or sell stock, the environment would be the stock market. And if you are playing Atari games, of course, the environment is going to be the game itself. So we have this, feedback loop between the agent and the environment. And now we have something called history, right? History is the sequence of observations, action, and reward. So basically, the history is in the point of view of the agent, right? It has seen this observation and also the reward. It's going to do some action, and then it will get the observation of the next time step plus the reward of the time step, and then it has to do the next action, and so on. So the history basically is the sequence of ORA, right? You have the observation, you have the reward, and then you have the action, and you just uh, put it in the same maybe in the same array or in the same sequence. So what happened next will depend on the history. So why do we need history? We need history because we want to be able to reproduce the current situation, right? At the start, right, for example, you are playing games, right? When you start the game, you are at O1, right? It's the situation in the O1. And if you have a history, you should be able to repeat this history and reach the same conclusion or the same situation or the same state. So our assumption is that if we have the history, we should be able to reconstruct the current situation after you have performed the entire sequence of history. So because of this, we can define a state function, st, to be a function of history. So this state is the state of all things, include the agent, include the environment, right? So the entire picture of the reinforcement learning can be captured in a state, right? As at the time step t. And if you give it a history, you should be able to reconstruct the entire situation from the sequence. And the state, right, as I said, they are the entire reinforcement learning situation can be broken down into the environment part and the agent part. And when we separate it this way, you can see the difference, right? So what is the environment state? The environment state is the internal representation of the environment, right? If you are playing the game, the constant in the game, the number of enemy in the game, the HP of the enemy in the game is the internal representation of the environment. And often, this information is unknown to the agent. So some of them cannot be seen by the agent. In the other hand, for the agent state, is the internal representation of the agent. So this is what the agent think the real environment would look like, right? And it will try to use this state to make a decision, right? So for a stock market, right, you don't know the internal work of the stock market, right? You don't know when this stock will increase tomorrow. You don't know which stock will go down tomorrow. But you can estimate, maybe you have the state representation of the stock price for each day, but you don't have the insight whether or not there may be some formula that if you combine everything, this stock will go up tomorrow. You don't know that function, but you can only see what is being shown to you. And this can be used for the algorithm. So in this class, we will focus on how to reconstruct, how to construct the agent state based on the environment, because we don't know anything about the environment, so we have to do the estimation. So we have the state, we have the reward. What about information state, right? Information state. So reinforcement learning have a very big assumption about the state of the entire thing. And that is, it have assumed that the step is Markov. What is Markov? Right? It's clearly the person name, of course. So we have this equation, right, for the condition for the state being Markov. So if the state being Markov say that the probability of you are in the state st1, given that in the past you are in state st, should be equal to the probability of going into this state st plus 1 based on the entire history. So what does it mean? It means that the future is independent of the past, right? So what determines the future? You only need to see the present. You don't have to see back yesterday. You don't have to see what happened a year ago. You only need to see today, and you should be able to predict tomorrow. So the Markov state is known as the information state. Basically, it contains all useful information from the history. And we have this red example, right? So what happened? So we have this entire situation, right? For example, the light is on, you pull the lever, you hear the bell, you might get sap or you might get food, right? So if all this happened at time t, right? So if the agent state is the last t item, right? You can see that, oh, this is the same. So what this should be, this question mark, the question mark should be the lightning, right? It's based on the agent state is t item. So if you define the agent state, if you see the agent state the same, for example, like these three set are the same, your future should be the same, right? Your future should be the same, right? So it doesn't matter what come before, right? You only look at what is given in the agent state. What if agent state is the count of light, bell, and levers, right? So we have, so the first one, right? You have two light, one bell, one lever. The second one, you have one light, one bell, two lever. The bottom one, you have one light, one bell, and also two lever. So what will happen at this question mark? You will get sheet, right? You will get sheet because it's the same state as this one before. So depending on how you define agent states, your result will should be the same if you are in the same state. So that is what it means to be Markov, right? You only look at the current state, and when you go to the next state, you don't care about what happened before. So in the perfect world, right, we call it a full observability. So in this situation, the environment is fully observable. So the agent state and the environment state are the same, right? So OT equal to SA and SE. And this is the case that we can model the environment fully. So basically what is hidden in the environment, we can see it. Everything in the environment is a public information, right? For example, you are playing, let's say you play poker, right? Each player have 5 cards in hand, right? For the poker, can you in this environment fully observable? You see your 5 card, but you cannot see your opponent 5 card, right? So there are hidden information that the environment know because they know which card everyone have and also what is in the deck. But for the agent, you can only see your 5 card. So that environment is not fully observable because what you see is only 5 cards, but what the environment see is the entire sequence of cards for each one, and also the sequence of cards in the deck, right? But if you play chess, right, every piece are on the board. Every position of the chess piece are on the board, right? What you see and what your enemy see is the same. So that is the fully observable environment. And when when the environment is becoming fully observable, we can call this process to be a Markov decision process, right? So not only that the future only depends on the present, but if we can model the environment completely, we can apply this Markov decision process. And we will start building notation for Markov decision process a little bit later. So the major component of the reinforcement learning, um, we have policy. What is a policy, right? So there are a lot of terms today that you have to memorize. So a policy is the agent behavior function. So what is the behavioral function? So basically the policy, right? If you have policy, you will send in the state, right? You send in the agent state, and then it will give me the action state at time t. It had to be right. So the policy is something that receive the state and then output what you should do, right? Sometimes it's not going to be just like one action. Sometimes it can be a distribution of all the action. Like for example, you should do this action 50% of the time, but you should do this action 30% of the time. So it doesn't have to be just one number out, like to be one action out. It can be a distribution over all the action that you can do. So that is the policy. The value function, the value function will tell you how good or how bad the state and action is, right? So if you are in this state, right, are you good or are you bad, right? Sometimes you can evaluate the current situation and tell whether or not you are in good state or in a bad state. Sometimes it's going to have this pair of the situation and also the action. In this situation, if you do this action, will it be good or will it be bad? So the value function is basically kind of like an estimation of the reward. Because you don't know the reward, you want to estimate the reward, right? Because if you can estimate the reward, you can estimate the future reward. And that will make your maximization a lot easier. So that is the value function, right? So basically it's the estimate of the reward function. And then we have the model. So the model is basically SAT. It's the agent representation of the environment. So that is the three component. When you write a code to do the reinforcement learning, you have to define these three components. So let's start with the first component, policy. So a policy is agent's behavior. It's a map from action, from the state to action, right? So you have A equal to pi s. And this is called a deterministic policy. So deterministic policy, if you give it a state, it's going to give you a single action every time, right? That is deterministic. If you have a stochastic policy, you send in the action, but you need to have a condition on the current situation, right? So in the current situation, if I do this action, it's going to tell me what is the probability that I should do this action, right? So how you define the policy would be different, but based on if whether or not you want it to be deterministic or you want it to be stochastic. And often enough, in many cases, we are going to use the stochastic policy most of the time. What about value function? So as I said before, value function is a prediction of the future reward, right? It's going to be used to evaluate the good and the badness of the states. And this will influence how you select each action, right? If you are in the bad state, you want to select an action that make the bad state into a good state. If you are good state, maybe you can select anything else. Maybe whatever you do will keep the state still being good. So that is the uh, definition of a value function. So we will do all these notation first so that you understand each component before we actually dive through the equation for each of the one. So we have policy, we have value function, and then we have a model. So a model, it will predict what the element will do next, right? So we have two model. We have model P and then model R. The model P will predict the next state, right? So it's basically the probability that if you do this action, what is going to be the next state? And R, the model R, is going to be the reward of doing the action based on the current situation. So in the maze example, right, I have the start and the goal position, and then I have this map for maze. My reward can be -1 per time step. So what does it mean to define a reward to be -1 per time step? So in this situation, I only define the negative reward. If we want to maximize the reward, what will happen? If we want to maximize the reward, I have to get as little as -1 as possible, right? And what will happen if you collect the least amount of -1? What would be the result? What would be the goal? So the goal is not just to reach from start to goal. What is the hidden goal? So not only that you want to reach the goal, you want to reach the goal fastest, right? Because the more time you take, you get more negative, right? At every time you are in the maze, you get -1. So based on this reward, basically you want to find the shortest path from the start to the goal, right? And what is the action? The action is basically you can go 4 directions, right? North, east, south, west. And the state can be agent's location, right? For example, if you start here, maybe you are at maybe 0, 1, 2, 3, 4, 1, 2, 3, 4. So you start at maybe 0, 3, right? That could be your state, right? So this is the um, how you define the reinforcement learning problem. And for the policy, right, what is the image of the policy? So the policy, you get the state in, you get the action out. So for example, if I want to make a deterministic policy, what is my state? My state is agent location, right? So my policy is going to be, I give it the location. You tell me which direction I go. And this arrow in the map is actually your policy, right? If I am in this state, what action should I do? I should go south, right? So for each state, I'm going to have one arrow. That is my policy, right? It's a function that whatever the state you give it to it, it's going to give you, it's going to tell you which of the action you take. So that is the policy. So the next would be the value function, right? How we can imagine the value function. So the value function is the estimate of the reward, of the future reward, right? The value function, if you give it a state, it's going to tell you how bad you are, right? How bad you are. And for the maze, how bad you are based on what? So the further you are from the exit, the worse you are, right? Because you want to reach the goal as fast as possible from the reward function. If you are far away from the goal, you are in the bad state. So the the square that are furthest away from the goal, right? For example, this square is going to have the lowest value function, right? So this function, if you are here, it's going to tell you, oh, it's 74. And this value function basically tell you that you need to take 74 steps to reach the goal. So that is the value function. So a model, right? So a model, the agent may have the internal model of the environment. So we can have the grid representation, the transition. So for us, we can only imagine the map, right? But for the agent, right, you have the state at 0, 3. Your action is going east. What is the next step? If you are at 0, 3, your action is going east. What is the next step? 1, 3, right? So this basically how the agent model the environment, right? Basically, it should be able to predict the next state based on the current state and the action, right? If it cannot calculate the next state, then you don't have a good model. So now we have a good picture of the reinforcement learning process. We start going to make a mathematical equation for each of the each of the component, right? So we have the policy, which is pi. We use pi for it. We have a value function. We use v subscript with pi, right? So based on your policy, your value function will change. So your value function will be based on the policy. And then you have the model, and the model can be represent maybe P and R here, right? Maybe it's going to be the intermediate reward or the transition function, right? And then we are going to define each of them mathematically. So we start with a Markov decision process first. So in the Markov decision process, right, what we have, we're going to build from the simplest process, it is Markov process, and then we will add the reward, and then we will add the decision, right? So before reinforcement learning, we only have Markov process, right? And when we have reinforcement learning, we actually start adding the reward, we start adding the decision. So what is the Markov process, right? So the Markov process, okay, we start with fun. So the Markov process is the memoryless random process. It's a sequence of random state with Markov property. So in the RL, right, when we define history, right, we have ORA, right? Right, we have observation, we have reward, and we have the action. In the Markov process, we only have this. We only have the observation. So we don't have any action. We only observe the environment, how it changed from one state to another state, right? And when you say memoryless, it means that, well, when the state is Markov, you don't have to keep the entire history. You only need to keep the current one, and then you can get the next one. That's why it's a memoryless. Like you just forget the past, look at the present, and then you can predict the future. So in the Markov process, right, we have two things. We have the state. This is a set of state, a finite set of state. And then we have the state transition probability matrix. So in the Markov process, we don't have reward, we don't have action. So the environment will change the state on its own. Like at each time step, the state is going to move to another state. And because we have many states, right? From one state to move to the next state, there is a probability, right? What is the probability of going from state 1 to state 2? What is the probability of going from state 1 to state 3? And we have this probability matrix. If we do the diagram, right? For this diagram, we have how many states? We have 7 states, right? We have 7 states, right? For example, we have state for, you play Facebook. They have state of going to class 1, class 2, class 3. Your ultimate goal would be pass, right? You want to pass the class. And the number that are on the arrow is basically the probability of the transition, right? For example, if you are at class 1, right, you have 50% of open Facebook, you have 50% of going to the class 2, right? So for each time step, the environment will change from one state to another. Okay. So far, so good. Okay. And we can, because we have this transition process, right? We can have something called a Markov chain. For example, if I start with C1, class 1, I can have many possible chains, right? I can go from C1 to C2 to C3, and then pass, and then go back to sleep. And then I can go from C1 to C2, so C1 to Facebook, I can also repeat the Facebook many times before I come back to class 1. So that are the sequence, right? So this one sequence is called an episode, right? So we have step, right? So step is when the environment change state from one state to another, and the episode is when you start with the starting state, and then you take a lot of paths, and then you finish at the terminal state, right? So in this one, the terminal state is sleep because there's no out arrow from the sleep, so that is your terminal. So all of the sequence that start with C1 and stop at the sleep, I will call it one episode. Okay. So that is the Markov chain episode. The transition matrix, you can model each number here, or the number on the arrow, to be in the matrix format, right? Basically, for example, from C1 to C2, you have 50%. So from C1 to C2, you just have the number 0.5, right? So you can change this diagram into a matrix format. So it's basically just a 2D array. And when you express the entire diagram into this matrix, later on, we can use the matrix operation to do the calculation. Right? It's easier to do things in mathematical format. So we have, this one is the Markov process. It's just a process from moving from one state to another. Now you want to add a reward to the process, right? So when we add a reward, we are going to have the reward and a discount factor. So the reward function at S, right, for the state X is the estimation, is the expected value of going to state, is the expected value of the future reward, given that the starting state is S. So R is the estimation of the future reward, right? So RS is based on R at the time step T plus 1. And then we have the discount factor. It's going to be the number between 0 and 1. So we have this R for each of the state, right? So if you are in the class 1, you have R minus 2. If you are in Facebook state, your reward would be minus 1. And if you are in the sleep, your reward would be 0. So we want to see if I start with C1, right? If I start with C1, what is my future reward if I start from C1? So from C1, I can go to Facebook, or I can go to C2, right? I go to Facebook, my reward is minus 1. To C2, my reward is minus 2. but each of them has the zero point 0.5 probability. So the expected reward, if I start from C1, right, would be 0.5 times minus 1 plus 0.5 times minus 2. So you get minus 1.5. So that is the R of the C1, right, would be minus 1.5, right? So if you start with uh, C1, right, your estimate would be 1.5. And because we are looking at an episode, right? One episode have many transitions from one state to another. And what we want to maximize the total reward. So you have not just one step, right? So this is the reward from one step, right? From C to the next one. I don't know which one you get, but on average, you will get minus 1.5. But I want to maximize the entire sequence from C1 to sleep, but I don't know what happened in between, right? So what I can do is I can write an equation for the gain, right? So the gain is the total reward, right? So it's basically is the sum of R, right? So the gain at time t is the R from t plus I onward. And we have this discount factor, right? This discount factor. The discount factor will determine whether or not you want the learning process to be a long term or a short term. If you want the process to be a short term, it means that you want to capitalize on the immediate reward. What is your immediate reward? Is RT plus 1, right? This is what you get at the next time step. So if you want to have the reward of the next time step to be the most important compared to the future, your discount factor should be close to 0, right? So if this one is close to 0, it means that you have put the emphasis on the immediate gain. But if you look at the long term, right, the long term sequence, you have to set the discount factor to be close to 1, right? It's called a far sight evaluation, right? So the close to 0 will put emphasis on the immediate gain. Discount factor close to 1 will look at the future, right? Put the importance on the future. So that is why we introduce the discount factor. So you can control how much you want, how far you want to go. So this is the example of how to compute the gain for the student MRP. So if I take the first sequence, right? C1, C2, C3, pass sleep, right? I go to C1, I get minus 2. I go to C2, I get minus 2. But because my discount factor is 1/2, I multiply by 1/2, right? And then you add up, you get something like minus 2.25. So this is the gain for this episode, right? This is the gain for this episode. So for each episode, you can calculate the gain. What about value function? So the value function Vs give the long-term value of the state, right? So the value of each state is the expected gain at time t, right? So the gain at time t is the sum of the future reward, right? Remember, you want to look at the future, and given that you are at the starting state would be this state, right? So if I want to calculate, right, the V of C1, then I would look at all of this episode, right? Each episode is going to have different gain, and each episode is going to have its own probability of happening. And so I just time this probability with the gain, and then I do the weighted average to find the expected value, right? However, it's going to be very difficult because there can be infinitely many episodes, right? Possible episode that you can take from C1 to sleep. So we have to do some estimation. We have to do something, right? We don't want to calculate it by default because we have many possible outcome, many possible way from going from S to the final state. So we will break down the equation, right? So the immediate gain, the gain at time t is basically this equation, right? So this is the same equation that we have, right? The definition of gain is the sum of the future reward, right? So we have the reward of time t plus 1, time t plus 2, time t plus t plus some, discount factor. And you can rearrange the equation, right? So that you end up with the reward of the next state or the next time step plus the discount factor times the value function, right? Times the value function of the next possible state. And when you write it this way, right? When you write this way, you can think of this as an iterative process, right? Because we want to find V of S, right? V of S for the every state, right? Maybe you can start with a random number, random value for each state. And when you compute the next state, you can use the current value and then you do some equation, some manipulation with the current report. So from this equation, right, what we have is that we are at the state S, right? We are at the state S. We want to find V of S, right? We want to find this value, and this S, right, have R probability. So basically, it's probability of going from S to S prime, right? And then S prime is going to have its own value function, right? So the value function we have for all of the states. And so this term, right, is the value of the next state. So you look at all the next state, right? sum of all possible next state that you can go from S, you time the probability of going to that state, time the current value of the current state of the state that you are going to. That is going to be your future reward. So in the example, right? So let's say you don't know this value. You want to know what is the value function of this state, right? You want to know the value of function of this state. From this state, you can go to this 1 and 2, right? There are two choices. The first choice, if you go there, you get plus 10. The second choice, you go there, you get 0.8. So the probability of you going to the first state is 0.6. So you have 0.6 times 10. So this 10 is the value function at the state 1, like this number 1. And 0.8 is the value function of number 2. And minus 2 is basically the reward at the current state that you are sitting on. So that is how you estimate the value function for each state. So basically, you do this multiple times, right? You calculate the value function, like new value function every time, using based on the previous iteration. And if you do it often enough, sometimes it's going to converge. Converge means that the value will not change, or the change is very small. At that point, you actually achieve the optimal value function. So the Milbank equation, right, from what we derive here, right, V equal to R1, should be the one, right? V equal to RS plus the sum of the property and then IS, right? This one can be represented in the metric format, right? So the value function, so we put all the value function into one vector. So in this case, we have 7 states, right? So our value function is basically 7 number, right? 1 for S1, right? So this one would be like minus 23, 0, minus 13, 1.5, 4.3, 10.8, right? So we have one number for each of the state. And this V, right, is equal to the R, right? So the R is this one, the reward of each of the state, right? So we put R in the one column vector, just like V. And then we have the discount factor times P. So P is the probability matrix, right? So if you want to go from state 1 to state 1, you have P11, right? If you want to go to state 5 to 6, you have P56. Right? And then you put it in the metric form, and then you multiply by V. So this is become the equation for the value function. And when you write it in the matrix format, it's going to be easier to solve, right? We want to know V, right? What is the value of V? So what we can do is we can move this term, right? Because we also have V into the left side, right? So this lone V, we can add identity matrix in the font, so that is the same, right? So what we get is we get I minus the discount factor time P, and then you have time V equal to R, and then you take the inverse of the matrix, right? So if it's a normal equation, you want to divide, right? But for the matrix, you left multiply the inverse, so that the front you only up with just V. So the direct solution is possible if you have the small process, right? So if this matrix, right, if this matrix is small, you can actually find the inverse. If this metric is not, uh, uh, normally the metric would be square, right? Because we have the row and the column would be the same dimension, right? You have 10 states, it's going to be 10 by 10 for the metric P. So they always be the inverse. But if the metric is really large, right? You have maybe 10,000 states, then computing the inverse might be time consuming. So that is how we add the reward to the Markov process, right? So not only just state with transition probability, but the reward for each of the state is also determined. And now we want to add decision, we want to add action, right? So up until now, from one state to another is happen automatically, right? For each time step, you have some probability of going to this state, right? And it happened automatically without you having to do any action. Now we want to add action into our model, our decision process. So this become a Markov decision process. And what we add? We add a set of action, A. So when we add the set of action A, all the metrics or the definition have to change slightly to account for this addition. For example, the state transition probability before we have one matrix, right? Now we are going to have multiple metrics and one matrix for one action. So basically before we have P S S prime, right? So the probability of going from S to S prime. And now we have A, right? So it's the probability of going from S to S prime given that you do action A, right? So you have add this extra layer. So your metric is no longer 2 dimension, it become 3 dimension, like you add the action at the end. This also happen to the reward function. So before we only have RS, right? Each state have its own reward, right? Going to this state, you get -2. Going this state, you get 3, something like that. But here, not only that you have the reward for each of the state, but it's also based on the action that you do. So it's not immediate that you are going to the same state, but you are coming from different state, or maybe you coming from the same from S to S prime, but you use different action. Even though you end up in the same state, you will not get the same reward. So each reward not only based on the state transition, but also the action that you make. The discount factor doesn't change, still the same. So now we have one extra layer for the process. So what can we do, right? We have to look at the equation that we have before, right? We have policy, we have value function, we have gain, right? How can we rewrite those equations to take account for this action? So we start with uh, the diagram first, right? So we have this diagram. We still have state, right? We have state. However, for each of the arrow, right? For each of the arrow, you have the action, right? You have the action along with the reward. For the simplified version of this, to make the process deterministic, we don't have the probability matrix anymore. If you are in this state and your action is Facebook, you are guaranteed to be in this state. There's 50% chance that if I do this action, I go to a different state. So if you are in a certain state, you do the same action, you should end up in the same state. And we have, how many actions do we have? We have Facebook, we have quit, we have study, and then we have sleep, and then we have pub. So we have 5 actions. Right? So as you can see, there is this state that doesn't have action. So some of the state will transition on its own without action. But if there is an action out from one state, it's going to go into one state, like a specific state. So you can have a mix, right, of whether or not you want the transition to be random. So from at this point, it go out at random. But for other point, if you choose the action, it always go to the same state. So we have to redefine our policy a little bit because we have action now. So before, our policy is basically deterministic, right? You give a state to do it into the policy, you get the action back. So the policy is now a distribution over action given the state, right? So in the policy, we define to be A and S, right? The policy of A given S is going to tell you what is the probability of you doing action A given that you are in the state S. So this policy will fully define the behavior of the agent, and it will only depend on the current state. Right? So for example, right? So the policy of maybe let's say this S1, right? The policy of am doing quit, right? Given that I'm in S1, this one is going to give me some number, right? So from S1, I have 2 actions, whether I quit Facebook or I keep browsing Facebook. So this value is going to tell me what is the property of basically the property that I should do this, right? So it can be like 0.6, the property of I still doing Facebook given S1 would be 0.4. So make sure that sum to 1. And this policy will tell you that 60% of the time, if you are in S1, you should do this action. You should quit Facebook 60% of the time. So that is the policy. In general, if you have the state transition as well, then the state and reward sequence, you can use the policy to calculate. So what do you mean by that? It means that, well, you want to go from S to S prime, right? You have to go from S to S prime. There can be many ways of going from S to S prime, right? You can do two actions. You can do A1 and it can go to S prime. You can do A2, it can go to S prime. And the way that you calculate the real probability of S to S prime, right? So basically, this one will calculate the probability of going from S to S1 regardless of your action, right? So when you say regardless of your action, you have to sum all of the possible action that you can do. So you sum all the possible action, and the probability of you doing this action will use the policy, right? The policy will tell you if you are in this state, what is the probability that you should do this action times the actual probability of going from one state to another given the action that you make. And the reward function is also the same, right? For RS, the reward at the current state. So you have to, again, you have to sum of the action that you do on this state, right? Of the action and the reward, right? Because of the definition, right? The definition have these three number, but we want to find just without action, right? We want to find the reward without action. You want to find the transition probability without action. And this is how you would do it, right? We use the policy to help with the weight when you take the sum of the reward given the action. Now for the value function, right? The top is what we have. The state value function, V pi, is the expected return starting from state S and following the policy pi. So again, before this, right? Everything you change state based on just the probability. But now you change state based on action, right? When you do this action, you are guaranteed to be in certain state. So when you have action, when you want to compute the value of that state, you have to use the policy to dictate the episode that you do, right? So the value function, basically, if you have different route that you can go, right? And the different route that you go will be based on the policy pi. So in another word, you can think of pi as our original transition. And about action value function, so the action value function, not only that you look at the action and also the state, right? So the state value function, basically you look at the state, right? And based on the policy that I have right now, right? The policy is basically what tell me what to do. Am I in a good state or am I in a bad state? Right. So that is the value function. For the action value function, I have both state and action. Right. If I am in this state and I do this action, how good it's going to be. So this one, you will do the expected gain, but based on that, the first action in the episode, in the entire episode, if you start with S, the first action you take is A, but the rest I don't know. So this slight difference between the state value and the action value, right? So again, one more time, the state value will tell you if you start with this state, are you good or are you bad, right? The action value, if you are in this state and you are about to do this certain action, it will tell you is it going to be good or is it going to be bad, right? So the action value will fix the first action in the entire episode. So let's see. So the state value function, I want to find the state value function for this one. So the red one is the value function. So based on this equation, right, you want to find the expected gain given that I start with S, right? So if I start with S, maybe I start with this one, and you use this to be equal to 1, then you have some policy, right, of choosing Facebook, and then you still get the reward -1. No, you get the future reward 0.2, 0.3. So for the state, right, you have, if I add this state, right, I can do Facebook, right, and then I can quit, right, and for Facebook, I will have R equal to -1 because I'm in the same state, -1, and then I would plus the gamma, which is 1, and then you have the gain of this one, right, which is 0.23. If I quit, I will have the reward 0, right, plus this discount, and then I get the value of that state, right, -1.3. Right, so I have two number, and based on the policy, right, if the policy of going to Facebook is 0.5 and 0.5, basically I take the average, but if it's different number, then you have to do the weighted sum, right? So that is the state value function when you want to do the calculation. And if I want to do the action value, right, if I want to do the Q based on the policy, let's say the policy is uniformly random of S, and the action, let's say I want to do the action Facebook, right? Right. For this one, right, I would have, I know that I'm going to do the action Facebook and set S, so I have to compute the gain given this one, right? So I take Facebook, right? I get the reward -1 because I'm in the same state, right? I get the reward -1, and then I plus the gamma times the maybe the Q value of that one. So the Q and the V is different number. So we have a vector for V, and then we have a matrix for Q, right? For Q will be S, A, right? So the column would be S, the row would be A. So this one times the Q of SA, right? Okay. It's gonna time S, let's see. So the expected gain from this given one, okay. So basically it has to be Q at the same state, but all of the action, right? I want to find the expected of all the action. So you have to use the policy, right? For each policy, for each S action one, you have S action two, S action three, right? And then you use this policy to compute the expected value. So that is the state value and action value, right? So that is the equation that I wrote. Basically, you have to do the expectation for all possible action of the future. Okay, so now we have these two functions. So basically this one will be like one-dimensional array. This one will be a matrix, right? So this one will be S, right? This one will be maybe S, this one will be A. So that is how you store this value in the memory. So for the actual calculation, if you want to find the equation for V pi, so x that S, right? I have this value function. I take action A, right? I take action A. I will have this action value QSA. Right? So we have VS and then QSA. So in these two, you can calculate one from the other. So if I want to know how good the state I am on, right? I can look at all of the possible action I can take, and then I can take the value of that action, right? The state action pair times the probability of doing that action, right? And that would be how good I am at this state, right? Because this from this state, right, um, you have this policy AS, right? The property of doing this action so that I take this action, and the quality of this action given this state is given by this Q. So you can calculate V from Q. And in the other hand, if I want to calculate Q, right, basically I'm in this state, I want to do this action. How good is it overall? And to know how good it is overall, I know that by doing this action, I'm going to state S prime, right? So from S to S prime based on action A. So I want to know whether or not this decision based on my current state is good or not. I look at the destination, right? So my destination is going to have the state value function, right? It's going to tell you how good this state is. So I'm going to take how good this state is times the probability that I'm going to this state with A. So if the first state is deterministic, you don't have to do the sum. It's going to be just this value, right? So it's going to be RAS plus R gamma V pi S prime, right? So this sum is only for when you do reaction A, you might end up in different state, right? If you are doing one action and maybe 50% of the time you go to S1, go to S prime, 50% of the time you go to S double prime, then that's when you do the when you need the sum. But if in this example, right, for each action, you know which state that you are going to end up with. There is no split. In this case, you don't need the sum, right? It will only have one term. And this probability of going to this particular state would be 1. Right? So you end up with this equation. Right? So we have the reward from this state, right? The reward from this state given A, and then plus the discount factor times the value of the destination state. So for this, right, we have two equations, right? We have V in terms of Q, we have Q in terms of V, right? So we have one equation for each of them. We can combine, right? So basically, we have this equation for Q. We substitute Q here, right? So basically this one, right, is basically tell you that, well, to compute V, I have some equation that I will use Q, right? And then this one, if I want to know Q, I have another function that will take V and then it will give you Q. So I just plug in this one, right, into this equation. So we have V in terms of F O G of Q. And this is this equation, right? So you are in this state, you take this action, there are some probability that I will end up in this state. There are some probability that I end up in another state, right? And then you take the V of the destination state based on the property here and also the policy here, right? This one will be the policy that will determine how much you want to do this particular action. And at the same time, you can plug in basically this equation into this term to get just a sole equation for Q. Right? Just plug in the equation, right? So we have this, right? So before it was V, right? It's before it was V. So V is this equation. So we just put in the equation as is. So with using this, you don't have to calculate one from the other. You can calculate the same matrix from the same metric in the previous step. Okay. And then this is the example of you going from you start from this stage, and whether or not you finish or you go to the pub, and then you have a different outcome. Right? So this is how you would calculate the value function. So to make it simple, there will be example at the end that we will try to do the calculation by hand together to make it more intuitive. But to summarize this process first, when you have the Bellman equation from before, right? We have V equal to R plus gamma PV. Now everything will have the policy as the dictation whether or not you will take this action to reach another state. And it will also have the same closed form equation. So the way that you solve the equation doesn't change. It's just that the way that you define stuff change a little bit based on the information about the action. And there is some theory about the optimal value function. So we believe that there exists, right? There exists a state value function that is better than everything else, right? So the optimal value V star, right? This is the best V that will tell you which state is good, which state is bad, right? Perfectly. And no matter, right, for every policy that you can come up with, the value is going to be the maximum over of the policy, right? So policy is the function that will tell what to do given the state. And also, we believe that the action value function, there exists the optimal one, right? The best one that when you give it the state and action, no matter which policy you pick, you have the maximum value. So the Markov decision process is solved when we reach this optimal value. And this optimal value, like for example, these are the optimal value. If we reach this optimal value, then we are solved, right? So this means that we can actually order the policy. We can compare the policy, right? So remember, ultimately, we want to find the best policy because the best policy will tell you what to do, right? You give it a state, it's going to spit out the action, right? You want this function for ourselves. We actually don't care about the value function at all. But the value function will help us determine whether or not this policy is good or not. So the definition for when you have two policies, right? We say that if the policy pi is better than the policy pi prime, if the value function for the pi is greater than the value function for the pi prime for every state. So at every state, I have better value function, then we can say that, okay, pi is better than pi prime. And for the theory, it says that there exists an optimal policy that is going to be greater or equal to pi for every possible policy that you can come up with. right? So this is the theory that they exist. And also not only just the optimal policy, but also the optimal value function and also action value function. So this is what they prove. This thing is already proven that they exist. I'm not going to go through all the proof because you have to understand the ordering, the partial ordering, and a lot of mathematical stuff, which I am sure um, you haven't done math for a while. So we are certain that okay, we sure to have optimal, right? But how can we reach the optimal, right? How can we find such pi that is optimal, right? So proving that there is optimal doesn't mean that you are going to find it, because in mathematics, right? When you prove something exists, sometimes you doesn't have to give a construction, right? You just have to prove that it exists, but you don't have to provide a way to compute it, right? For example, when you when they prove that there are infinite number of prime, they don't give equation of computing the next prime. But the proof is that when you start with a prime, you can always find a bigger prime, right? And they just give a construction for that bigger prime to prove that you can always find the bigger one. But they don't give the equation for finding the next prime because it's impossible, right? So proving that something exists doesn't mean that you have a way to find it. So because of this, we have to do some learning, right? We want to learn the policy, we want to learn the value function, we want to learn the uh, state action value. So if we know the optimal for Q, right, then the policy can just be, one if it's the maximum, right? Basically, you look at Q, you look at all of the possible action, whatever the highest, that will be the action for the day. So if we know the optimal Q, we will know the optimal pi, and so on. So what this means is that if you know one optimal, right, between we have pi, we have v, and then we have q, right? So if we know one of them is optimal, then the rest will also be optimal. So you only need to find one. So we have to find, okay, which one is the easiest to find the optimal? And I'm going to pass on this because it's basically the same equation, but this is when you already have everything optimal. So to solve the optimality for the Millman equation, well, it's not linear, so there is no cost from solution. So basically, if you have the optimal, right, all these functions become maximum, right? You take the maximum, and the maximum function is not linear, right? It's not linear at all. So that's why you cannot use uh, the inverse, right? Because it's not this anymore. It's basically max v pi, right? You use max v pi for this. So if you use max v pi for this, right, you cannot do anything, right? You cannot find the inverse for the maximum function. So it's clearly cannot be expressed in a matrix format anymore when you take the maximum. And so we have many ways to solve it. Um, we can have the value iteration. We could have a policy iteration. So basically, we um, go to each iteration of value function. We compute the value function at every time. Also policy, and then we have the Q learning. So let's say that if we know pi, Q, or V, like if we know one of these is optimal, everything else is optimal. So of course, the solution will be focused on one of them, right? So value iteration will focus on the value. Policy iteration will focus on the policy, and then Q learning will focus on the Q, right? So we have a set of algorithm for each of the components. And the one that we are going to learn in this class is Q learning, right? Turn out that Q learning is one of the easiest among the three. So that's why we will learn it first. So Q learning, what is Q learning, right? So we want to learn Q. So Q have the form of S and A, right? So for each state, if I do this action, what should be my value, basically? So for Q learning, right? For optimality, I take the maximum of all the actions, right? Minus, so this is the action of the future state minus the action of the current state, right? And I want to estimate this action value function. I will take one step at a time, right? So I start with the original value. I have some alpha, right? Right. So I start with SA, right? SA will give me a reward, right? Give me a reward. And now I'm in S prime. And this S prime, I don't know. I don't want to use the value for S prime because this Q learning, we only want to learn Q. We don't want to learn pi or V. So we have to go one step further. So we know that we are in the next state, right? We are in S prime, the next state. In this state, we have to go into each of the action from S prime. And if you want to find the best possible action, right, you take the maximum between the Q of this state based on this action, right? And you take the maximum and then you minus. So this is basically this is basically almost cancel out based on the alpha. But the original equation is that, well, you get a reward. You want to plus the future reward. What is your future reward? Your future reward is going to be, well, you are in the new state already. If you want to maximize your future reward, you better pick the action that will give you the highest value. So you take the maximum of A prime for every possible action on your S prime, right? So this is the equation for the SA, the QSA. This is the Q learning. So the Q learning control the convergence to optimal action value. So if you do this operation many times, it should convert to the optimal Q. So we have a pseudocode. We are going to write code next week. This week is going to be, just the explanation. You initialize QSA. Basically, you don't know the Q any, you don't know the Q any of the Q, so you can randomize it. You have this value for any Q, right? You can randomize any value or you can have anything, right? And but for the terminal state, you have to set it to 0. Because when you are in the final state, there's nothing else to do. You have reached your conclusion, so the value should be 0. And for each episode, right? So this is important for each episode. So when I say for each episode, it's not for each step. You have to repeat it until you finish the episode, right? So the episode you start with, I don't know, sub S, right? And then you repeat for each step, right? For each step of the episode. So from S, right? From S, you choose action A. From S, using policy derived from Q, right? So even though we use policy here, we actually do not use the policy function. We use the current Q value, right? Because the current Q, like this one, you take the maximum, basically you take the argmax of all the action, right? Based on the Q of S and A, right? So this is basically the policy. This is actually the policy, right? So you have S, you will choose A based on the policy, right? So whatever give you the highest Q value at the current step, you're going to choose this action. And once you take the action, right? You take action A, you get reward R, and you are transition to S prime, right? So you are at S, you take the action based on the policy that depend on Q. You are in the S prime, right? So you get the reward, right? Not only just you are in the S prime, you get the reward. So after you get the reward and you know that you are in the S prime, you will update the Q value of S based on A, right? The Q value of set S and action A to be the original value plus some alpha. So alpha here is basically a learning rate, right? This alpha here is the learning rate. So the learning rate time you are expected Q value if you pick this action, right? So you get the reward R, and then you compute your expected gain, right? From this state. And then you transition to the next state. And then you repeat this process until S is terminal, right? Until you reach the terminal state. And then you finish one episode. And then you could repeat the next episode the same way, right? You can initialize any S, right? You can start with any S, and then you can do the entire process again. So that is the Q learning. So here I say when you shoot action A from S using policy, there is one strategy that you have to learn. It's called epsilon greedy. So if you only use the policy, if you only take the maximum, right? If you only take the maximum, it's become a greedy algorithm because you always take what is immediately highest to you. But for epsilon greedy, you want to take action based on policy, but not always. So in greedy policy, right, you want to uh, choose the action value with some probability, right? For example, if I take the epsilon to be 0.1, so 10% of the time I choose random action, and 90% of the time I choose base action, right, based on pi. So this is epsilon greedy, right? So you don't want this to be just pure greedy. Sometimes you want it to take a random action. And the reason being is that when it take a random action, we call it exploration, right? Because depending on your starting value, right, you can you might get stuck in the local maximum. So when you take something random, you are exploring the option that is not optimal, right? Because perhaps you have, let's say you have A1 and A2, and you start A1 with 5, you start A2 with -2. But it turned out that A2 should be the maximum one. So if you use greedy, the algorithm will almost always choose A1 repeatedly until the number go down, and maybe it will go down to maybe like 3. But if you choose A2, maybe it can go up to 7 for when it reaches the optimality. So you want it to sometimes take a random action, so it will try something different. And just like learning rate, right? In the early episode, when you know nothing about the environment, you know nothing about the queue, your initial queue is very bad. So this epsilon can also change over time. It means that at the early episode, you can have high epsilon, like you want it to explore as many options as possible. But as the time go on, the epsilon can decrease, and you want to take the optimal solution more. You want to take the optimal action more because you are now certain about your Q value that is going to give you a good result. So that is the reason behind why we pick greedy policy, right? Right. So this is the epsilon, right? So you take um, with the probability epsilon, choose action at random. When epsilon, you take the greedy action. So that that is the epsilon greedy policy. So as I say, right, is so reinforcement learning is about trial and error, right? In here, you take action. You don't know is it good, but when you take the action, you get the reward back. And if you have a high reward, your Q value is going to go up. But if you have a low reward, your Q value is going to go down, right? And that will dictate your future decision that, oh, if I'm in the same state, I used to do this action, but I have a very low reward. Maybe I do different action instead, right? So that is the mindset of the reinforcement learning. So in the exploration, you want to find more information about the environment. And the exploitation, if you want, if you already know a lot of information, you want to only maximize the reward, right? So it's important that you start with exploration and then you end up with exploitation. So for the example, right? For the restaurant selection, right? Your exploration can be you try the new restaurant, but if you want to do the exploitation, then you go to your favorite restaurant, right? The restaurant that you are sure that you are going to enjoy. So for the demo, I will save it for next week. Um, so what I want you to review, basically review uh, this algorithm as well as the update function. Also, this diagram, right? To be able to understand what's happening in this diagram, you start with that if you want to do action A, what happened next, right? So for reinforcement learning, that's why good for game, because in the game you can picture the future, right? You shoot a laser, you know it's gonna hit or it's not gonna hit. So for next week, we will try different um, environment for the reinforcement learning algorithm. So the first half is going to be the one that people already implemented for us, and then we can use that environment. Mostly, there is like the card poll um, example and also other environment. And then in the later half, we will use the environment in the last assignment. So if you can read the assignment, just read and then try to understand what is happening, what are the state, what should be the action, what should be the reward before coming to class. That would help a lot, because in the description it will tell you the rules of the game, right? The rule and then the goal of the game, but it doesn't tell you how to write a reward function, right? Because remember, the reward function is the mathematical formula that when you maximize it, it should translate to your goal of winning the game. So there can be many reward formula, and I expect everyone to have different one. So it's better to understand the game rule first before coming to class next week. So that's all for today, and I will see you next week. Thank you.